פול טינג'יי הוא מהנדס יישומים בכיר לחדשנות בזמן אמת מחברת RTI. נושא ההרצאה שלו, GVA, ארכיטקטורת רכב כללית.
Hi there, my name is Paul Tingey. I'm a field applications engineer from Real-Time Innovations based in the UK. I'm going to do a short presentation on DDS and its role in the generic vehicle architecture. I'll give a quick overview of what GVA is, what GVA includes, and then explain why DDS was chosen for its particular role within the GVA architecture. So the generic vehicle architecture was first published back in 2010. It's actually a UK Ministry of Defence standard for open vehicle architectures. Everything that I'm going to talk about, by the way, for the next few minutes is best thought of in the context of the UK generic vehicle architecture. Other countries, other nations have created derived versions of GVA, and some aspects of the way that they use DDS in those derivative versions is slightly different, and I'll try and explain those as I go through these slides. So what's included in the GVA standard is, for example, how to connect equipment together, how that equipment connects over the network, all of the data items that are included within that architecture, and things like the look and feel. There's some mechanical and electrical parts of the specification as well that are included in GVA. Inside of the generic vehicle architecture standard, it actually says these words. So the specific purpose of GVA is to realize the benefits of open architectures, specifically to improve operational effectiveness, to reduce risk and to reduce the cost of ownership of vehicles that use the generic vehicle architecture. What does GVA include? This image is lifted directly from the UK version of DDS Standard 2309, which is the GVA standard. It describes the separate components that are connected through the data distribution service, DDS, and their specific roles within the vehicle. And you can see from the green boxes that are shown on here, those are the the DDS parts of the system, that not all parts of the system actually use DDS for low-level control. But there are specific parts of the architecture where DDS is actually mandated. In fact, in the GVA standard, what is mandated is what's called DDSi, which is the DDS interoperability protocol, otherwise known as RTPS. That's the low-level protocol on which DDS works. And also in the specification, it specifically says that this is not vendor specific. The GVA components are completely vendor agnostic, as is DDS that's used within GVA. But DDS is the mandated middleware layer, the logical bus that connects all the separate subcomponents within the generic vehicle architecture based vehicle. If we turn the previous diagram over and we look at it a slightly different way, this is actually how GVA vehicles are architectured. And as you can see, the orange part on the left-hand side, which shows DDS, doesn't cross the whole vehicle. There are other components within the vehicle that use other network technologies. For example, MILCAN, which is a ruggedized CAN bus architecture, is used for all the automotive interconnects within the vehicle. TTP, or Time Trigger Protocol, is used for time and mission critical data. In the UK, there is a separate DEF stand called 0082, or VIVO, which is essentially carrying video over Ethernet using more traditional protocols such as RTP and SAP. What this means is video data is not carried over DDS. Now, that may be different in other nations that have derived versions of GVA. They may be serializing video data in the form of DDS and moving that over a DDS architecture. But in the UK, that's not the case. What DDS doesn't do is manage time. So NTP is used for time management in the context of this system. And then DDS is used for connecting all the DDS specific applications within a GVA vehicle. Some of those applications are legacy, in which case some form of DDS adapter may be needed. So why was DDS chosen for GVA? DDS fulfills a number of important principles that are embedded into the GVA specification. For example, openness. DDS is a completely open standard. It's managed by the OMG, and it fits really nice with that principle of openness within GVA. DDS enables modularity, and that's really important within the context of a GVA vehicle. And it also enables scalability, and that's another thing that's embedded in the GVA specification. There are some other technical advantages that I'm not going to cover too deeply in this presentation, but for example, performance. DDS enables real-time performance, and that fits really nicely with some of these components that are used in GVA vehicles. If we first look at open standards, DDS is an open standard. In fact, it's a whole family of open standards. There's 10 or a dozen different standards that cover various different parts of DDS. Everything from security to the wire protocol is specified within a standard, so that any vendor can create products based on these standards. That fits really nicely with the GVA principles of openness. OMG defines the standard. In fact, it defines two things within the standard. The DDS standard itself defines the wire protocol that's called RTPS, or real-time publish subscribe. That's mandated as part of the GVA spec. And also in the standard, there's an API that's called DCPS that enables portability at the vendor level between different code components. DDS itself is completely platform agnostic, so you can run on any form of CPU and OS. There's multiple language bindings. In fact, in most cases in the military and defense realm, it's either C or sometimes C++, but the standard allows language bindings for almost any language. And all of this is available from multiple vendors. DDS also enables modularity. So if we imagine a simple DDS-based system, DDS is actually a middleware layer. It sits between what we tend to call a platform and the application layer, which is shown here in blue. DDS manages data on behalf of the application, and it abstracts you away from the platform that you're running on. Each module within a DDS system, so if you imagine this to be a GVA vehicle, each of the DDS-based submodules will be running their own instance of DDS. They will interconnect with each other. They will discover each other. They will understand the environment that they're running within. And each application uses the API that's provided by DDS to publish and subscribe to data that's available across the whole system. The sum total of all of that data that's available within the system, we call a data bus. This is a term that you see very often in the DDS world. It's a virtual concept. It's a global shared data space within which many items of data are available, shared between each of these different DDS instances. One of the other features of the data bus is when a new node, a new subsystem comes online, it will discover its environment. It will use various aspects of the RTPS protocol and discover its environment and connect and fix up all the connections based on publish and subscribe mechanisms. Equally, that node could disappear and DDS will again repair all of those connections and make notifications where needed. There's a number of things happening here. First is there's a data model. So in order to do all these clever things, DDS needs to understand the data. You provide that understanding through a data model that's usually written in IDL, and that's true in the GVA case. In fact, GVA has its own data model. It's called the land data model. That describes all of the data that could exist within a generic vehicle architecture vehicle. And that allows DDS to manage that data as it moves around the system. Data is published into data streams that we call topics. While the data model describes the data in the system, quality of service settings describe how that data is moved around the system. Quality of service settings are encoded into the land data model to define what data is, for example, reliable or best effort, or whether you want particular history saved for particular data items within the system. What DDS is doing here is it's promoting location transparency. All of these systems are interested in publishing and subscribing to data. They're not really interested in where that data is coming from or going to. They're just interested in the data itself. This modularity allows decoupling of system components and redundancy. You can have multiple subsystems that provide redundant data. DDS has built-in inherent modularity to allow you separation of modules. For example, if they have different safety certification levels, and it allows easy maintenance and expansion of the system. And remember here that DDS has no central server. There's no central server or broker to fail. There's no single point of failure. And that allows a really reliable system. Scalability. DDS is built on the principle of data centricity. In other words, the interface is the data itself. Applications just read and write data, and the underlying infrastructure, that is DDS, understands and manages that data. This is very similar to a database. So in a database, you store and you search through old data, as in the SQL syntax that's shown on the left-hand side. On the right-hand side, you can do a similar thing with DDS by sharing and filtering future data and enabling that data to be delivered to particular nodes only when it's of interest to them. This scalability allows this kind of parallel by nature architecture, enables peer-to-peer connectivity and many thousands of nodes. This picture here is the NASA launch system that has hundreds of thousands of nodes, each communicating via DDS. There's a number of other advantages, which I'm not going to cover in any depth here, but performance and faster development are also critical to the GVA environment as well. The other advantage of DDS is it enables connectivity beyond GVA itself. DDS is used in avionics and naval systems and simulation systems, and data can be bridged between these different systems, enabling, for example, security and data filtering along the way. So you can interconnect all of these different systems through DDS to enable modularity at a very high level. And that allows you to build very advanced distributed simulation systems. So, for example, you can connect a DDS-based GVA vehicle through a bridge, maybe through a secure bridge, to other systems that maybe allow other kinds of sensor data, to asset tracking systems and other simulation systems, to web-based systems through a DDS bridge, and even to other types of simulation systems like HLA, through an HLA to DDS gateway. And in that way, you can build up highly advanced simulation systems that include GVA-style vehicles as part of that simulation. Okay, thank you very much.